Okay, so I've got a program here called tHookProc. That's part of Matt Conover's code injection tools. It actually doesn't recompile very well with Visual Studio 2005, so I recommend using the binary build of that. All the rest of this stuff does compile with Visual Studio 2005. And the reason why you want Visual Studio 2005, of course, is that there's the free Express edition. You can see here that I'm running a program called listenonpipe.exe with a parameter which is name of the test pipe. Maybe not now. Name of the test pipe, and the name of the test pipe, that's the pipe it's going to create. So my library that I'm going to inject is called namedpipespy.dll, and that's the thing that has my hook in it that's going to overwrite the start of create name pipe. So I run that, and down in the window where I executed it, you see a whole bunch of stuff coming out of the tool that hooked it, just saying, oh, that worked, because I practiced this demo, and it works. This little window that popped up is actually the listen on pipe process, and what it does is it just says, hello there, I'm going to be using this name, my PID is foo, press enter to begin listening. And so when I hit enter, it's going to start listening on that name pipe, and our hook's going to become activated. So I better run the program to log the output. So now I've got this call logger started. Call logger is just a program that's going to receive the message. So when I hit enter, over on the call logger I see the name of the pipe appear. So this little string that said name of test pipe Bob. So I can create any number of pipes and have that log them all. Now if I wanted to make it a little more interesting, I could include SDDL and other information about the pipe that said what the ACL was that it was created with, so that you could figure out if this was part of the attack surface of the program. Remember that even pipes that only allow one connection at once and immediately have the client connect have a race where users with low rights users could try and connect up to it. Oh, and those low rights users could be remote. So, injecting a middle person. So now that we've injected a spy, we can think about injecting a script in the middle. The script in the middle is going to do something like hook the creation of the IPC mechanism and launch a fuzzer and move data back and forth. So the normal flow is you have a server, and the server wants to create a name pipe to let connection, or to let clients connect up to it. So it says to the kernel 32, hey, I'd like to create a name pipe. And the pipe's name is foo, and the kernel says, sure, here you go, and it gives it a name pipe. And then the client connects to the pipe, and everyone's happy. Well, when we've got this hooked, the flow changes a little bit. The server calls kernel 32 and says, I'd like to create a name pipe named foo, and the hook receives the call instead of kernel 32. And the hook says, well, I'm going to just launch this middle person script. So it does a shell exec on a Python interpreter in our example here. And now we can write our actual fuzzer in Python, which is a lot easier than writing a fuzzer in C++. You have, it's just a easier language to do string manipulation or fuzzing. My partner Scott Stender is going to be doing a presentation this afternoon on internationalization attacks. And one of the things he'll do is talk about, he's got some code where he shows a bunch of different ways of doing car set attacks. Really cool stuff. You could take those car set attacks right out of his Python code and dump them into this, and then use that fuzzing technique on this attack surface. What the middle person fuzzer does is it goes ahead and it creates the name pipe that the server wanted. So it says, hey, kernel 32, can I have a name pipe called foo? Sure, says the kernel. Then the hook says, all right, I'm going to just change the name of the pipe that we create on behalf of the server to bar. And then the operating system gives the actual server back a different pipe. Now the server doesn't know that it's been given the wrong pipe. It just thinks that, oh, my call succeeded. I know I passed in foo. If it wants, it can go and look in that buffer and see if it's still called foo. It is. We didn't actually change it. But the client doesn't know that the name of the pipe has changed. And so the client still connects up to foo, and the fuzzer just forwards the reads and writes along to bar. And optionally, it can modify them. And actually, it can even tell which ones it should modify. It can tell, for example, if this is a read-only pipe, that the only thing that's worth modifying is the output, right? And so you just modify the output. If it's a duplex pipe, so it allows information transfer in both directions, which is one of the flags in the mode that you specify when you call that create name pipe function, then it can modify just the input and fuzz the server. And if you want, you can tweak the Python script so that it's targeting the client instead of the server. So I'll give a little demo of this. I'm not actually going to exploit some piece of code and have a 0-day here. I'm going to just do a little fuzzing demonstration on a sample server. So I'll set up a little server that just shows the data that it's receiving from its client, and I'll set up a little client that writes data to it, and we can see that the data is being modified by the hook. Oops. All right. So I'm doing the same thing I did before with the T-hook proc. I'm launching listen on pipe. This time I'm calling the pipe test pipe, and I'm injecting, instead of the name pipe spy DLL, I'm injecting the name pipe redirect DLL. That's my little C hook that changes create name pipe so that instead of just calling or creating a name pipe, first it launches a Python script, tells the Python script, hey, here's the new name and the old name of the pipe, what the modes were, what the, which direction the data is going to be flowing, any parameters it needs to create an equivalent version of the pipe. Then my script creates its own pipe, and the hook changes the name of the pipe that the server is going to create to something else. In this example, it appends underbar original to the original one and lets the client create the one that was expected. Sorry, the fuzzer create the one that is expected by the client. So when I run this program, the first thing that happens is that listen on pipe.exe pops up. This is my listening program. So this is my server down here. The actual hook is just reporting back, yes, I successfully injected myself and it's been activated. So when I hit enter here, it's going to start listening on a name pipe. And so I expect that what's going to happen is a Python script is going to be spawned that is going to be doing the fuzzing on any data that goes through this pipe. So I hit enter, and up pops this little window with a happy little snake in the corner. And the window says, hello there, this is the Python script spawned by the hook. I'll be accepting client connections from whack-whack.whack-pipe whack-test-pipe, and I'll be redirecting the reads and writes to whack-whack.whack-pipe whack-test-pipe original. And it logs a seed, which is useful for resuming the fuzzing, and lets you know that the client pipe's been created. So now we need a client. Here's the server. This works better on a high-res screen. So my client is just a tiny little program that writes to any particular pipe, any file, once a second. So the file I have here is abc.txt. It's the alphabet, so you can easily spot if it's changed anything. And I think it's in all uppercase. So it's going to just repeat, write that once a second. So I hit enter, and up in the server, immediately we see the alphabet being sent once a second, and it doesn't look quite like the alphabet that I would normally expect. Maybe this one right here is totally unchanged, but I've got a very high change rate, so I'm doing a lot of random fault injection into this data that's coming in. Now, in an actual example, you might lower the chance of the injection occurring, and you might change the injection so that they have things that are specific to the domain of your application, but you don't have to. You can just go with this. And if I kill the client, it stops, and when I restart the client, oh, you'll notice that over here in the hook, I got a little exception, but now it's resuming because I restarted it. So as long as I send and receive data in here, I'll keep getting little exceptions in the hook, and the pipe will keep seeing fuzz data. All right. So one of the things that's nice about this approach is that the Python code at least, or actually all the code is fairly simple, but the C code's simple because you don't have to rewrite it every time. You can just reuse it over and over again. The Python code's also totally reusable if you want to do the simple kind of thing that I've done here. If you want to do some customizations like adding in Scott Standard's internationalization fuzzing, you can do that by just changing the Python, and the Python script can be actually really simple. All you need to do is create a name pipe with the name that's passed in, listen on it for connections. When connections come in, pass them off to the server, make any changes you need. And so what kind of fuzzing do we want to do? Well, we just need to decide what we want to change. So the obvious and simplest thing to do is just randomly inject faults. Change random values. It says A, I say B, whatever. Maybe shorten and lengthen the strings randomly, which is one of the other things this does. You can try incrementing and decrementing values. That's really helpful for looking for fence posts. Inserting large numbers, so it's really good to write at least one, all binary ones into every offset inside of the message, at least once when you fuzz it. So you might even do it in a window to move through, because what you're looking for is things that take offsets, untrusted offsets. Like people move structs sometimes through these things, so that's not safe. You might want to overwrite all the nulls to see what happens when strings get really big. You might want to overwrite the double nulls to do the same thing with Unicode. This is all standard fuzzer stuff. You can do anything you want. You can change the size of the writes so that they're enormous. You can null them out. You can do things like look for a username, and when you see the username occurring anywhere in there, add some garbage. Mix it up. The ideal rate of change lowers over time. So when you first start fuzzing an application using this, you might find that if it's fruitful, you might find that you get bugs right off the bat. And as the engineers come back with you with patches, usually you want to lower the rate of change so that you can get deeper into the protocol. If you've got a sophisticated protocol with a lot of different messages going back and forth, you might need to get in pretty deep before you inject the fault if you want to find kind of deeper errors in the logic. Usually when you inject something that the server isn't expecting, it's just going to close the connection on you. So, if you never let it get very far without injecting an error, you won't get it to fuzz the deep parts of the protocol. Another tip is to, all these fuzzers are based on something random that you do. Well, it's not really random, it's pseudo-random. So that means if you restart with the same seed value, you can generate the exact same changes to the input. So if you use the same data set, you run the same server, you use the same seed, you should get the exact same flow. That's really important for reproducing bugs. Now, sometimes you're going to have things like, oh, this thing's based on, this thing's a, I don't know, it's some kind of weather satellite monitoring application, and every time it looks, the atmospheric conditions are different. So the data is always different, and so you can't actually repeat it that way. Well, that's fine. Another technique you can use is just log all the traffic that travels through the pipe. Say, oh, the server said this, the client said this, here's a transcript, and then you can actually just write a very simple script to replay the client side of the transcript. And you can sometimes do fault injection. I think in the sample tools that I ship, there's a simple pipe fuzzer that doesn't actually relay a transcript, it just kind of writes random junk, but it's the same kind of idea. You could do that and base it on what the simple transcript was from at least one side of the conversation.